Okay, for this problem, we are going to look at yet another problem for determining an equivalent circuit. Um, and here we have a 15 amp power supply connected to a resistive circuit. And we're looking for the Thevenin equivalent or the Norton equivalent circuit between the two output terminals right here. And what's important to note here is that the output terminals are separated from the 15 amp supply by these resistive elements. So we know that in order to solve for the Thevenin or Norton equivalent circuit, we need to determine the open circuit voltage as well as the short circuit current when the two output terminals are connected directly with a wire. So one way that we could approach this would be to look for the open circuit voltage by solving for the node voltages. And that's a fine method to use. I'm going to take a slightly different approach because we can solve for the node voltage right here at the top of the 15 amp supply, but that still doesn't give us the open circuit voltage between or across this 12 ohm resistor. What we could do is we could establish node voltage equations for this node, and this node with this as our reference node, and determine what the potential is at between the 12 and 10 ohm resistor with respect to ground, as well as the 2 and the 12 ohm resistor with respect to our ground reference, and take the difference between those two. But a slightly simpler approach can be had by recognizing that this circuit here has two meshes, and to use the mesh current method, what I'm going to do is establish two meshes here. And you'll see quickly that because we have a 15 amp supply in one of the meshes, we already know that IA, that mesh current, is 15 amps. We don't have to do any work to solve for that. So we'll have one equation to solve for this unknown mesh current, IB. I've assumed that both of these currents are going in the clockwise direction, so we need to write our equations accordingly. So IA, we know, is already 15 amps. All right, so now all I need to do is to perform my Kirchhoff's Kirchhoff's voltage balance for this mesh right here. All right, so for mesh IB, I'm going to assume that IB is the dominant current. First, I'm going to look at the current flowing through this 8 ohm resistor. All right, here, IB is going up, and IA is assumed to be going down. So they're counter to each other. So I'm going to have to subtract the magnitude of IA from that, multiply by our 8 ohms. Okay, I already know that IA is equal to 15 amps, so I'll substitute that in just a minute here. All right, now I need to know the direction, or I need to know the potential developed across the 2 ohm, the 12 ohm, and the 10 ohm resistor, and I know that the same current flows through all of those. Also, based on my schematic, I know that that current does not interact with any other mesh currents anywhere else in those three resistors. So the potential developed across all of those is going to be the sum of the 2 ohm resistor plus the 12 ohm resistor plus the 10 ohm resistor. All of that multiplied by IB has to sum to 0 volts because there's no external voltage supply in this mesh. Okay. All right, so I can go ahead and substitute my 15 amps in here. All right, and when I do that, what I'm going to wind up with is an equation all in IB, and I can solve directly for my mesh current IB. I should find that my current IB is going to end up being 3.75 amps. With that in hand, now I can directly solve for the voltage, or my open circuit voltage in this case. I know that my current is 3.75 amps. I'm going to multiply that by my 12 ohm resistance, which is where the open circuit potential is developed, and that's going to give me the open circuit voltage. So my open circuit voltage can be calculated by taking this current, IB, multiplying it by the 12 ohms of resistance. 3.75 times 12 gives me 45 volts of potential for my open circuit voltage. All right, so just want you to recognize that sometimes it may be more advantageous or easier to go ahead and solve for a voltage using the mesh current method. Okay, so now that we've determined that the open circuit voltage is 45 volts, we need to move on to determine the short circuit current, as if we connected our two output terminals together directly with a wire. I want to know how much current runs through that wire. Alright, so again, I'm going to establish some reference directions for my meshes. And it doesn't really matter which direction you're going to assume for these. I'm going to actually assume that IB goes a different direction this time, just for the fun of it, and to demonstrate that it doesn't matter which direction things go. Alright, so I'm going to assume IA and IC are both going clockwise, and IB is a counterclockwise current. Alright. Again, the potentials that are developed are going to be different because these two terminals are connected directly with a short circuit. We also do not have to directly solve for IC. What we could do is just recognize that no current is going to flow through this 12 ohm resistor here, and we could just completely remove it from the circuit and solve for that directly. But I'll just want to show you that even if we don't make that assumption, we still get the correct results. Alright, so we already know, again, just like last time, that since there's this 15 amp current supply in here, that the current in mesh IA has to be 15 amps. Alright. Now I'm going to write my voltage balance for mesh B. Alright, and that's going to tell me that the potentials developed across the 8 ohm, the 2 ohm, the 12 ohm, and the 10 ohm all have to sum to 0 because there's no external voltage supply here. Alright, I'm going to start off with this 2 ohm resistor. The only current that's flowing through that 2 ohm resistor is IB, so IB times 2 ohms plus, alright, now I'm going to move on to my 8 ohm resistor, and since I've assumed that my current direction for IB is going in the same direction as IA, I know that those two are going to be additive, so IB plus IA is going to give me the potential developed across the 8 ohm resistor. The only current flowing through the 10 ohm resistor is IB, so IB times 10 ohms. Alright, and the way that I've assumed my current direction here through the 12 ohm resistor is that both IB and IC are additive. So I'm going to take IB plus IC, multiply it by my 12 ohms. All of that has to sum to 0. Alright. For my IC mesh, the only thing that I have is this 12 ohm resistor in the IC mesh. Alright. And since I've assumed that the directions are opposite of each other for these two, IB flows in the same direction as IC through that 12 ohm resistor, so again they're additive. IC plus IB multiplied by 12 ohms also has to equal 0. Okay, so we have two equations to allow us to solve for the two unknowns IB and IC. I can plug in 15 amps for IA because I already know what that value is. I'll let you do that on your own, and when you do that, you should determine that the short circuit current, which is the current in mesh IC, which is also the Norton current, is equal to 6 amps. Okay, so with this information now, since I know the open circuit voltage and the short circuit current, I can determine the equivalent resistance for the circuit. So the Norton or Thevenin equivalent resistance is the open circuit voltage divided by the short circuit current, which we have found to be 45 volts divided by 6 amps, which results in a equivalent resistance of 7.5 ohms. So again, this circuit can be represented in two different ways now in a simplified manner. We can represent it as a Norton circuit, which is a current supply of 6 amps in parallel with a 7.5 ohm resistor. Alright, so since this current, 6 amps of current when there's an open circuit flows through here, we will have the 45 volts of potential developed across that open circuit. And anything that we connect here, any resistive load that we connect between these two terminals will operate in a manner, will cause the circuit to operate in a manner similar, or exactly the same, excuse me, as this circuit that we were solving. The other way we can represent this is as a Thevenin equivalent, which is a voltage source, and that voltage source is going to have a magnitude of 45 volts, and that's going to be in series. This Thevenin circuit is equivalent to this Norton circuit, which is equivalent to the original circuit that we started with. They will all behave mathematically the same and can be used to model each other.